Now we turn to what a graph really is. Let's learn the core vocabulary that every representation is built on. This graph has 6 vertices, numbered 0 through 5. It has 7 edges, and each edge is an unordered pair of vertices. A vertex is a thing, or a node. Here vertex 0 is Ada, vertex 1 is Ben, and so on up to vertex 5, which is Phe. An edge is a connection between two vertices. The edge 0, 1 means Ada knows Ben. Two vertices are adjacent when an edge joins them. They are neighbors. Vertex 0 and vertex 1 are adjacent. Vertex 0 and vertex 5 are not. Incident is a word for an edge and each of its two endpoints. The edge 0, 1 is incident to vertex 0 and to vertex 1. The degree of a vertex is the number of edges incident to it. The degree of vertex 2 is 3, because it has edges to 0, 3, and 4. This graph is undirected. The edge from U to V means the same as the edge from V to U. Every edge here runs both ways, because knowing someone runs both ways. And two counting terms. The order is the number of vertices, which we call N. The size is the number of edges, which we call M. This graph has order 6 and size 7. A quick check. Using the graph above, what is the degree of vertex 3? Pause and count. Count its edges. It has edges to 1, to 2, and to 5. So the degree of vertex 3 is 3, the same as vertex 2. There are 4 words for a root along edges. Each one is stricter about what may repeat. This figure is 2 triangles that share vertex 0. Vertex 0 has degree 4, so 4 edges meet there. A walk is the loosest root. Vertices and edges may both repeat. An example is 0, 1, 2, 1. A trail is stricter. Vertices may repeat, but no edge is used twice. An example is 0, 1, 2, 0, 3. A path is stricter still. No vertex repeats, so no edge can repeat either. An example is 1, 0, 3, 4. 2 more terms, both for closed routes. A circuit is a closed trail. It returns to the start and uses no edge twice. On the 2 triangle figure, an example is 0, 1, 2, 0, 3, 4, 0. A cycle is a closed path. Nothing repeats except the start and the end, which meet. An example is 0, 1, 2, 0. Notice the rules only get stricter. Every path is a trail, and every trail is a walk. The circuit we just named goes through both triangles at vertex 0. It is closed and repeats no edge, but it does revisit vertex 0 in the middle. So it is a circuit, but not a cycle. Because a cycle is the closed form of a path, and a path never revisits a vertex at all. Let's trace those same 5 terms on this chapter's own graph, instead of an abstract example. This is the reference graph, with vertices 0 through 5. Its highest degree is 3, at vertices 2 and 3. For a walk, take 2, 3, 2, 4. The edge 2, 3 is walked twice, there and back, and walks allow any repeat. For a trail, take 1, 3, 2, 4, 5, 3. Vertex 3 is visited twice, but its 3 edges are each used only once. For a path, take 1, 0, 2, 4, 5, 3. It uses all 6 vertices, none repeated. That makes it a Hamiltonian path on this graph. For a circuit on this graph, take 0, 1, 3, 2, 0. It is closed, it repeats no edge, and it only revisits the start. And for a cycle, take exactly the same route, 0, 1, 3, 2, 0. It is closed and repeats no vertex except the start, which equals the end. Those two rows show the same root on purpose, and it is worth knowing why. The highest degree on this graph is 3, so no vertex can be revisited in the middle of a root. That would need a degree of 4 or more, which means every circuit on this graph is also a cycle. The earlier 2-triangle figure uses a degree 4 vertex on purpose. It is the one place in the chapter with a real circuit that is not a cycle. There are two ways an edge set can get messy. A simple graph excludes both of them. This figure shows both problems. Vertex X has a self-loop, an edge back to itself, and vertices Y and Z are joined by two parallel edges. That makes this a non-simple graph, called a multigraph. A simple graph has no self-loops, and at most one edge per pair of vertices. A loop, or self-edge, is an edge from a vertex to itself. It adds 2 to the degree of that vertex. A parallel edge, or multi-edge, is 2 or more edges on the same pair. Any of those makes the graph a multigraph. This course assumes simple graphs throughout, and that assumption pays off immediately. It is exactly why a matrix cell holds a single 0 or 1, and why a pair appears once per chain. No counts to keep, no duplicate links to track. There are 2 extra features an edge can have, and each one is independent of the other. Neither one changes the vocabulary we just learned. They only add information to an edge. The left figure is directed. Each edge is one way, shown by an arrow. Here the arrows run from shower to dress to leave, with an extra arrow from shower straight to leave. With a directed edge, the arrow direction is the meaning. The edge is not reversible. Degree also splits in 2. In degree counts the arrows coming in. Out degree counts the arrows going out. For example, leave has in degree 2 and out degree 0, and shower has in degree 0 and out degree 2. The right figure is weighted. Each edge carries a number. A road map's weight is a distance. A network's weight might be a cost or a capacity. This chapter's running example is undirected and unweighted, the simplest case. But every idea here extends directly. A directed graph just sets one matrix cell instead of 2, and a weighted graph stores a number instead of a 1 and marks a missing edge with a sentinel, 0 or infinity when 0 is itself a real weight. A graph does not have to be one connected piece. This small picture has 3 separate pieces, a triangle of 3 vertices, a single edge, and one lonely vertex. Each separate piece is called a connected component. A graph is connected when a path joins every pair of vertices. From any vertex you can reach any other vertex. A component is one maximal connected piece. For a directed graph, strongly connected means you can travel both ways, and weakly connected means connected once you ignore the arrows. A tree is connected and has no cycle. Its number of edges is exactly the number of vertices minus 1. A forest is a set of separate trees, one tree per component. A dia-G is a directed graph with no cycle. Its vertices can be put in order, which we use in chapter 16. And a complete graph has an edge between every pair of vertices. For a simple undirected graph, that is n times n minus 1 over 2 edges. For a directed one, it is n times n minus 1. One word pair matters most for the rest of this chapter. A sparse graph has few edges, roughly the number of vertices. A dense graph is nearly complete, with roughly the number of vertices squared. That single difference is the main thing deciding matrix versus list later on. Workload matters too. Frequent edge tests favor the matrix even on a sparse graph.